So in this tutorial, I'll be showing you how to make this very basic prototype flight system, which increases speed when you go down, decreases speed when you tilt up, has roll correction, so it'll automatically restabilize. And you can control it with either the mouse or the keyboard, whichever one you prefer. It has collisions with the ground and is ready for lots of expandability. You can extend this functionality out. It is entirely in C++, but there's some functionality that has been made available to be viewed and expanded upon in blueprints. So here we are in a blank C++ project. I have starting content in mind, just that I have a little bit of something to work with. You're going to want to go and create a new C++ class. You can create yours as a character or a pawn. I'm making mine as a character because I want to be able to extend it later. And we can call it whatever you want. I've called mine Flyer, and I've already gone and created it. And in the C++ classes folder, under the name of your project, there you'll find your C++ class. And if you double click on it, you will open it up in whatever your code editor of choice is. Rider comes bundled with Unreal at the moment, which is very handy. It's a very good code editor, and you can get a free trial of it, still kind of in beta, until February next year, so that's well worth signing up for. If you open that up, this is what you will see. You'll see the C++ project, the file, and the header file. So the header file is where we kind of set up the base functionality of the class, and then the actual C++ file is where we implement it. So in that header file, let's see here, we are going to want to set up a couple different variables that we're going to be pulling from to calculate our flight system. So one of the variables that we're going to need is a float acceleration and float max speed, float min speed, and let's see. Then we're also going to need a float current speed, current forward speed, I think, just so we're a bit more specific. Current forward speed, and then we'll throw in a couple variables for calculating and controlling our direction as we move. So that will be float, float current yaw speed, current pitch speed, and you guessed it, current roll speed. And then I think I'm going to instantiate these with some basic, oops, wrong brackets. There we go. Some basic numbers, just so that we can start them with a little bit of something. I have some numbers based off of my own testing, but you can come up with whatever ones you want. You can use these values and then change them later if you want to. Current forward speed, if we start off with a value, then that means when the player is instantiated, they will have a starting speed, so they're not just going to start from nothing, which is what we want. Okay. So then what we need to do, now that we have some variables set up, is we need to set up some different functions that are going to actually make use of some of these variables that we've created. In this prototype, I'm wanting to process the movement of the controls both by the mouse and by the keyboard, so the player can choose which one they want to do, whether they want to control with the mouse or control with the keys. That adds a little bit more complication. There might be an easier way to do it, but this is the way that I found to implement it. So we're going to create a function. We're going to call that process key pitch. We're going to take in a float of the rate. So that's when the player hits the key for adjusting the pitch. That is the rate that we're going to adjust. And then we actually need to, now that we've processed those values, we need to apply them to the rotation. So for calculating the actual rotation. Okay, so now that we have some of these processes, these different functions, we need to implement them. So in Rider, and probably in Visual Studio as well, I can just go to the process, generate implementation, and it will create the actual function over in our C++ file. It's very nice. So now we can go over to our C++ file and we can actually start working with these, but we don't have any input yet. So what we have to do is in the C++ file, we go down to where it says the setup player input, and that is where we actually configure what the input keys are for our player. So before we do that though, we need to hop back over into Unreal and go into the project settings, which you can find file edit and project settings. I already have mine open. Scroll down to the input, and here you'll see action mappings and axis mappings. Action mappings are things that are more like just button presses, whereas the axis mappings can be a bit more flexible in terms of different values. And then it'll be a little bit different for the keys, because the way the keys work with axis mappings is 0 is not pressed, 1 is pressed. And so we need to have them as separate mappings, and we'll adjust it by the rate so that we can get a little bit more control over it. So it's not just a 0 to 1, but it kind of flows in a little bit. So now we have turn, lookup, turn rate, and lookup rate. We can go back into our flight system, into the C++ file where we bind our inputs, and we're going to bind these inputs to the actual controls. So what we need to do is go player, input component, do a nice little arrow, and we do bind axis. We're going to bind the axis that we have just defined. So we have 4 axes. We have lookup, lookup rate, turn, and turn rate. So we'll do the turn is the name of it. And then the object that we're wanting to bind it to is this C++ object that we have created. And then we want to set it to be a flyer, which is this one. And the function that it's going to link to will be process key roll. No, process roll, process mouse. That's the mouse one. Process mouse x input. There we go. And so then we're going to want to basically copy this. Okay, so we have just bound those keys to these functions. So when these keys that we have defined here are pressed, it will trigger these functions. Except the way it works in Unreal is that they're always being called, whether they're giving a 0 or a 1 is the question. So we need to take that into account as we're going through and setting these up. That these are being called pretty much all the time, and they are calling a 0 if the key is not pressed. The mouse input, from what I can tell, works a little bit differently, but I'm still figuring all that out. So what we're going to do is for the process keys, So process key roll and process key pitch, we're going to want to control whether or not it actually sends the value on to the next thing. So what we're going to do is an if, and then fmath, because we want to access some of the basic math functionality. ABS, which is absolute, so that will return this rate, and it will return the absolute value. So if it's -1, it'll say 1. If it's 1, it'll say 1. So it'll always give the positive absolute value of it. So if the absolute value of it is greater than 0.2, so if it is actually pressed, then we want to process roll. Oop, process pitch. Can't get those confused. And so the pitch that we're going to process, we're going to pass in the rate, which is whether the button is pressed or not, of how much that's pressed. But then we're going to want to multiply it by a little bit. Let's multiply by 2.f, just because trying to make it as similar as possible to the mouse inputs. You can play around with this value, find what works for you. But it's just there's a little bit of a difference between the way the keys work and the way the mouse works as far as how much the rate or the value is. So when this process key roll is hit, so if there's anything coming into the rate, it will pass that on to the process roll or process pitch. So then for the mouse inputs, we can just pass it straight on. So process pitch and value. Okay, so now the mouse will always be triggering, the keys will only be triggering if something is actually pressed. So that just kind of controls the flow of things a little bit better, because I was running into some issues where there was zeros and actual values being overriding each other because they were being called at the same time, the roll, the key presses and the mouse inputs. So now we need to process the actual roll and process the pitch. Let's go through and process the roll. So what we're going to do is simply do current roll. Roll speed, which is a variable that we set up over in Flyer. See current roll speed right here. So current roll speed, and we'll set that equal to fmath. And we don't want to jump it straight to the value, we want to kind of interpolate to it. So finterp 2, so that will do a smooth interpolation, so it won't jump straight to that value, but it will smooth over, which will create a lot more of a nicer look. So we want to go from the current roll speed, and we want to go to the target roll speed, which we haven't set up yet. So we need to target roll speed, and the time that we're going to want that to, the delta time that we want that to take is the time that the last frame has been, so that way it's frame independent. So the way we get that is we do get worlds, and then we stop it. Get world and get delta seconds, and that will return the time since the last frame. And the speed that we want to go, let's just do 2.f. And that is the speed at which it goes from the current roll speed to the target roll speed. So we need to set up the target roll speed, which is a float target roll speed, and we will set that to the value. But the value was actually going to be pretty low. So what we want to do is multiply it by a multiplier. So we'll set up a roll rate multiplier. And that roll rate multiplier, we need to actually stick it in somewhere. So we can go back over to the Flyer H, and we need to set up a roll rate multiplier. Let's just drop it in right here. Float roll rate multiplier. And I think I will instantiate that with a value of about 200. And we'll see if that gives us the result that we want. So that multiplies the input by 200. So here we have this value coming in, but the actual value is not Ah, did I? That value is not going to be very high, and so we multiply it by this roll rate multiplier because we don't like magic numbers. We want to be able to actually control the numbers that we see. And that is what's going to get passed into here. And we don't want this being edited anywhere else, so we can just set it to a const just because keep things a little bit more safe and clean. And so just like we have a roll rate multiplier, we're going to want a yaw rate multiplier as well. Float yaw rate multiplier. I'll set that one to 200 as well. I'm doing these as separate ones just in case we want to have a bit more control over the speed at which we turn versus at which we go up or down. This way we can kind of keep those separate and be able to tell. Control that a little bit more. So for the pitch, I do not want target yaw speed. Not sure where that came from. So let's do pitch rate multiplier, not yaw rate multiplier. Congrats to those of you who picked that out. There we go, pitch rate multiplier. So now we have the roll and the pitch being processed, and we need to actually apply that to the character. So in the tick, which is going to be called every frame, that is where we will implement the actual thrust and the rotation of the player. We will calculate the, let's just do the rotation first to see if it's working. We're going to need a new F rotator. We're going to call this delta rotation. This is the rotation of this frame. 0, 0, 0. Instantiated at 0. Then we'll do the delta rotation dot pitch, and we'll set that equal to our current pitch speed times delta time. You'll notice that we had to do get delta seconds over here, but because we're actually in tick, they have the delta time available for you to access right here. Then we just simply add actor local rotation and add in delta rotation. So what we're doing is we're creating an empty F rotator. We're applying the pitch, the yaw. Oh, I already applied the pitch. Ah. Let's do roll on this one. Current roll speed and delta rotation dot roll. There we go. And then we're applying the variables that we set up here, processing the different inputs. And then we are applying that rotation to the actor. And theoretically, that should give us the basic rotation that we want. So let's save this and hop back over into Unreal. We want to take our flyer class, we want to actually create a blueprint from it so that we can derive from that to add a bit more functionality that's a little bit easier to access. So create a blueprint class based on flyer, and I'm going to call it flyer underscore or BP underscore flyer. Some naming conventions go in there. And here is our basic flyer. If we wanted to, we could have set up a lot of these things in C++, but some of these things are just easier to set up in the actual blueprint editor itself, I find. So we have capsule component, arrow component, mesh, and character movement. The mesh is currently nothing. So if we wanted to set it to something, we could, but we don't have any skeletal meshes available to us at the moment. So what I'm going to do is I'm just going to add cube This is the front of the plane, sides, back. If we go to our self here, we can't actually see any variables, but we'll fix that in just a minute. So we'll compile, save, go back to the default view, and then here we're going to want to set in the world settings for this level, game mode override. Let's see, we should have created a game mode, but we can just go and create the C++ classes, C++ flight system. There is a game mode base that is right here. We can create a blueprint class derived from that, and let's just call that my game mode. So what we want to do is the player default pawn class. We want that to be BP flyer, and that will make it so that our player is the one that is instantiated into the level when it instantiates the level. So in the world settings, game mode override, we want to set it to my game mode, the one that we just created. So now we see there's a player start here in the level. So if we go to play, it might do something, but it probably won't yet because we still need camera. So we will add a spring arm and a camera. So what this allows you to do is have the camera extended beyond the player kind of on a string, and you can set all kinds of damping and stuff like that. I'll put this about 500 back and target offset 100 up on the Z. We'll leave it like that for now. Just kind of see what happens. So then you're going to want to compile. I'll pause my recording while I do that because my computer can't handle it. Okay, so it has finished compiling. So now if we hit play, we might see something. Here we have, woo! Okay, so it's rotating left and right, it's tilting up, and it's tilting down. And it's doing it with the mouse as well. Okay, mouse up, mouse down, mouse left, mouse right. Keyboard right, keyboard left, that's reverse. And up and down. Okay. So the turn rate, let's reverse these. -1 and 1. Reverse these as well. Actually, I'm okay with the controls like that. So now if we go back over to the flyer, go to the character movement, an issue that you might have is that the default land movement is walking. Let's just set it to flying for now. Flying. So that we can, we don't have to worry about it catching on the ground and not being able to take off once we actually add thrust. Okay, so that is working. Let's go back over to our code. And we want to expose some of these variables into the blueprint so that we can actually see them and edit them in over there so we don't have to do it all in code. And so what we're going to do is add some U properties to these variables. So a U property, you add a U property, it basically, Unreal will run through these U properties, and depending on what they say, we'll expose these variables in different places in the system, whether you want it accessible in blueprints or only visible, or different things, it'll do that. So we want these to be edited anywhere. We're not super protective of these right now. And we'll give them a category called flight. Okay. I'm gonna copy this. I want the acceleration to be visible. I want max speed to be visible. Min speed to be visible. Roll rate multiplier and pitch rate multiplier. Yeah, I'll make those visible as well, just in case the designer needs to access those. Current forward speed, that's handy to see, but I don't need to edit it. I don't want to edit anywhere. So instead of edit anywhere, I will do visible anywhere. So you can see it in Unreal, but you won't actually be able to edit it. Okay. So now if we save and compile this, we'd be able to see it in the editor in Unreal. But I don't want to do that quite yet, because I want to do a little bit more work here. So in the tick, we have the roll working, but we want to add some movement to it. What we're going to do is at the top of the tick, we're going to calculate the thrust. So we'll make a float of the current acceleration. And this is just a handy little function that I found. Get actor rotation dot pitch, and then it will multiply that by delta time, and multiply that by acceleration. And so what this line of code does is it takes our pitch, whether we're tilting up or we're tilting down, and it adds speed based on that. So if we're tilting up, we'll slow down. If we tilt down, we'll slow up. Depending on what angle we tilt, we'll slow up or slow down or speed up faster or slower. So now we need to calculate the new forward speed. So we'll create a new float for that. And that will be the current forward speed and less the current acceleration. So we're adding our increase of speed or decrease of speed to our current forward speed. Our current forward speed will be equal to fmath, and we're going to clamp it. So what clamping does is it makes it so that the value does not go above or below this these variables that we've set. So we take the new forward speed that we've just created, and we don't want it to go below the min speed, and we don't want it to go above the max speed, which are variables that we set over in the header file. We have the min speed and the max speed. And then once we have that, so these can be set to const. It wants me to do that just because we're using them here. We're not using them anywhere else. We don't want them to be edited anywhere else, just to keep them a little bit safer. The same, we'll do a const f vector, and we'll call this one local move. And this will be a vector that we'll make. This is current forward speed, because we want to move in that direction, times delta time. And then the other variables, the y and the z can be 0 because we don't actually want to move on any axis except forward at the moment. This could all be changed later if you want to expand the system. So we add actor local offset, and we do local move. That's the location to move to, and we set sweep to true. What sweep does, I have parentheses here. What sweep does is it means that if this movement collides with anything, it will stop the movement. So it's not going to go through walls and stuff like that, which is what we want. And now, just because it's handy to see what we're actually working with, let's just add a little debug message. So the engine, add on-screen debug message, and the key will be 0. We don't have any other debug messages right now. Time to display, I'll just put it to 0.f. It's going to be updating every frame anyways. F color, set that to, what's a good color that we'll see? Green. f string f. So here is where we put in our text. Text that we want to put in is, oops, I parentheses around these brackets. So forward speed, and then we want to add a float variable in here. This is getting quite long. Forward speed, and we will do f float, and outside these brackets we'll put current forward speed. Make sure I got all my brackets in the right places. Okay, so what this does is the key of 0. So this is a specific message, and it will override itself every time it updates. For a specific amount of time, in a green color, it will display this text debug message that will, because we've put in a little float value, this is the current forward speed that we'll be displaying right here. So if we save this, save these, and I realized I made a mistake. All these variables that we had put here in the generated body of the header don't actually go there. Whoops. So we'll put them here, default values for this character's properties in the constructor. And now, in the right place. So if we save this, hop back over to Unreal, and compile the project again. Okay, now that that is all compiled, we go over to our flyer. You can see at the top there's a category called flight. These are the variables that we set up in that header file. And so we have the acceleration, max speed, min speed, roll rate, and current forward speed, which is grayed out. We can see it, but we can't edit it. And any of these, if we edit them, set this to something other than 30, then it'll tell us that it is not the default, and we can only just reset it back to the default. So that makes it nice for testing things out and getting functionality working. So we now have the player in the scene, but let's make the scene a little bit bigger so that we can see a little bit more what we're doing. This, I'm gonna scale it up by 200 on that. Good. Okay. So now if we play this, okay, very confusing because it doesn't level off, and the camera is way too close. Let's fix some of those things. We go over to the BP flyer, go to the spring arm. Let's adjust some settings on this. So we want the inherit roll to be off. I want it to inherit roll. I want to enable camera lag, enable camera rotation lag, and let's drop the lag speed a little bit so it lags behind a bit further, and the max distance, we don't want it going more than, say, 500 away from the player. Now, if we compile that, save that, play. Colliding with the chairs here, that's what our problem is. We need to change the rotation at which we start. The camera goes further away, and it's not following us. Then we go up, we go slower. It kind of catches up to us, and that is just a complete mess. So let's go to player start, and let's move that away a little bit. Change the rotation so that the player starts facing somewhere other than straight into the chairs. Okay, so that's better. But we also want to make it so that the player corrects themselves. the roll, so that when they're rolling, it automatically rolls back when you're not pushing the buttons. So do that. Just want to set up a couple variables here. 2 booleans. Intentional pitch, set to false by default. And intentional roll. I'll also set to false. And these booleans we will use to help tell us whether or not we're intentionally pressing the keys, whether or not whether it's supposed to correct the rotation or whether it's not supposed to correct the rotation. So if we go to the process pitch, we want to set up this intentional pitch here. So intentional pitch, and we'll set this one similar to how we did it in the processing of the keys. We want to do fmath absolute value, and we want to see if the absolute of the value is greater than 0. And so the intentional pitch will be true if there is any value coming into the pitch. And if there is no value coming into the pitch, we're not pressing up or down, we're not moving the mouse up or down, then this intentional pitch will be false, and it will trigger some things that we'll set up now. So now in the roll, we want to set up a similar thing. Intentional roll, and that we'll do the exact same thing with that. Fmath absolute value is greater than 0. This is where things get interesting. If let's say we're doing a loop and the intentional pitch is true and we're upside down, we don't want it to roll back because we're intentionally flipped upside down. So we need to do an if statement to tell whether or not we should continue on with this function to calculate the roll or not. So if intentional pitch is true and intentional roll is false, then we want to return out of the statement. We don't want to do anything with this. So if we're intentionally upside down and we are not intentionally trying to turn, then it will return. So now that we have that set up, if we are intentionally trying to, if we're not trying to turn, then it will correct its roll. Hopefully this will make sense when we actually test it in the game. Okay, so that is the self-correction mechanism. Save this, jump back into a reel. In our flyer, we have a couple settings that we still need to adjust. So in the, to set the use controller yaw be off. So what we actually need to do here is change this target into a bit of an if statement. So what we're going to do is, instead of just doing, if this is true, do this thing, we haven't actually put in our self-correction system. So we'll do be intentional roll. Will then be dependent on this. So this statement is a bit of a shortcut for something else. But what this statement means, actor rotation dot roll times -2f. So what the statement means is that if intentional roll is true, then do this first thing. If intentional roll is false, do this second thing. and the target roll speed will be set to whichever of those is chosen. So it's taking a couple if statements and converting them into one line, which I appreciate. So now the target roll speed, all that's good. Let's go back and compile one more time and see how that goes. Okay, the compile has completed. And so now if we go and play, the self-correction, self-roll correction should be working. So we roll, turn, and it goes back. And if we intentionally try to go, it'll roll back and it'll self-adjust. So then if we flip upside down, it won't correct itself. But if we flip upside down and leave it, it'll just flip back over right side up. Same thing for if we do it with the keys, same effect. But now, the last thing that we want to fix is the fact that when we collide with stuff, it's not working quite the way we want it to. So right now, you collide with something. Let's see if I can just get over here. Just kind of stick into it until you break away, and that's not what we want. Our speed keeps building as we drive down into something. We need to put a little bit of control on that. So what we're going to do for that is a little bit more complicated, and I'm just stealing this from the flying template game that Unreal provides. So what we're going to do is make a hit virtual void notify hit. And so this is in the header class, and this is a very long thing that I need to set up here. That is a very long function. So now we will implement this in our other class, our C++ file. Here we go. They shortened it down for us, which is nice. So now, in this collision event that it's going to trigger as soon as we collide with, say, the floor or a wall or pretty much anything, and we want to override some stuff, and okay. So now we're going to deflect along the surface. So we'll need an F rotator, and we won't need to access it anywhere else, so we'll set it to const. F rotator, current rotation, because we need to set that so that we know how we're rotating when we strike the surface. Get actor rotation. Then we need to set actor rotation based on that collision. So we'll do a quaternion function, which this is spherical lerping between two different quaternions. So we need to take the current forward speed and the minimum speed, and then we're going to get the delta time. So once again, that's get world and get delta seconds. And then the speed of that interpretation will be 0 to 5. I found worked good. And I'm not doing it. I got confused on which line I was on, because I am basing this off of another document that I have open right now. So we do not actually want to do it this way. we want to slurp between the current rotation dot quaternion. So make sure we get the quaternion of that, and the hit normal to orientation quaternion. Which what that does is let's see what that does. Does it tell us? Might tell us another time. And then that will be the 0.25, or 0.025 rather. And one more bracket. Okay, so now we need to actually do the slowdown. The current forward speed is equal to fmath f terp2. This is the current forward speed to the min speed delta seconds, and the rate will be 5. Yes. So this is just the same basic. Let's see, get world. Let's see. Point. So this is the same basic interpreting linear interpretation to the from the current speed to the minimum speed. So you're slowing down to the minimum speed at this rate. If you collide with something. So now we'll save this. Save this. Go back into Unreal and compile and test it out. If we play, you should see that when we collide with something, kind of deflect off that surface, or kind of like bouncing off of it almost. Okay, so we need to turn. Our speed gets down, and depending on what angle we deflect with the surface at, we're kind of rotating to deflect off of it. So we go faster, and slow down until we deflect off the surface, which, because our minimum speed is 500, that's, yeah, it's a little bit harder to see. So this is a very basic flight system. It's dynamic in the sense of being able to increase and decrease speed based on the pitch. You can rotate. It will self-correct its roll when you want it to, which makes for some easier control. You can do loops. The camera follows, pulls further away when you're going faster, and it lags behind you a little bit. There's some basic collisions set up, which slow you down. The rate of that could probably be adjusted. But this basic functionality, you could go on from here to implement things like boosting and throttle. You can add my own project. I can add animations and all that sort of stuff to it. You can add stopping and going, different states. You could add landing, whatever you want. But this is the core functionality, a base to build from.